In this problem, we're going to determine the voltage V0, and you can look and see where V0 is labeled at this point in the circuit. We've got two ideal transformers. As a result, we're going to use our problem-solving strategy entitled Circuits Containing Ideal Transformers. And if we look at that, we're going to be reflecting things through transformers. And since we want to solve for V0, what we'll do is we'll take everything in this side of this transformer and move it into the middle, and we'll do likewise for this transformer. So we're going to reflect everything into the middle here. We're going to eliminate both ideal transformers. So if we look at our strategy, and it says look at the relationship between the dots and the voltages. Well, we really haven't got any voltage here, but let's go in and label this one, for instance, V1, V2, and let's label this current I1, this current I2. So if we look, for instance, the voltages are both referenced with respect to the dots. So we'll have here, we'll have V1 over 1 is V2 over 2, or V2 is equal to 2V1, and then we got one current defined entering the dot, the other current defined leaving a dot. So we have I1 equal 2I2. So now we're going to reflect through. So when we take this voltage source through, we're going to multiply it by 2. So once we reflect it, it'll become 100 at an angle of 0. And then we're going to multiply the impedances by the turns ratio squared. Turns ratio is 2, so it's going to be 4. So this is going to become 8 ohms, J16 ohms. So now we've reflected it. So let's now look at our circuit with everything reflected. So there's our circuit now. And now we need to work on reflecting things through. This time, again, we don't have any voltages really defined or currents, so we're free to define them how we choose. So I'm going to define voltages here, V3 and V4, and then current I4 and I3. And if we look, now we've got the voltages. One's defined positive and undotted terminal, the other's defined positive, the dotted terminal. So we get V3 over 4 is equal to minus V4 over 1. So V3 is minus 4 V4. And if we look, we got one current, both currents defined as leaving dots, so really we get 4I3 is equal to minus 1 times I4. So when we move things through, our impedances get moved by turns ratio squared. So this becomes 8 ohms, this becomes minus J8 ohms. This becomes minus 40 at an angle of 30. Now what I'm going to do is I'm going to take and redraw it. I'm going to change the polarity and change it to plus on this source. So now when we get through and reflect all that, here's what we have. Notice now I took my voltage source and changed the polarity because it was minus 40, so I just changed the polarity. Now we can analyze this circuit. Again, this is a single loop circuit, so we can define a current I, and if we go through and apply KVL, we'll have 32 plus J10 times I is equal to 100 at an angle of 0 plus 40 at an angle of 30. And it tells us that I is equal to 4.06 at an angle of minus 8.9 degrees. And if we calculate V0 now and say, well, let's go around this loop to do that, then V0 is 14 minus J16 times I minus 40 at an angle of 30, and V0 then is 93.68 at an angle of minus 83 degrees.